Hello, welcome back to the geography class. Today we are going to see storm hydrograph. At the end of this video, should be able to define the terms related to storm hydrograph, should be able to draw and label the storm hydrograph, should be able to highlight areas which are in high risk of flooding, and you should as well be able to explain factors affecting storm hydrograph. The storm hydrograph can simply be defined as a geographical graph that shows the effect of rainfall to the river's discharge, or how the rainfall affects the river's discharge. And normally this effect is positive, and the river discharge is the amount of water flowing in a river channel. It is measured in cumex. Cumex is a cubic meter per second, and on that graph, on x-axis, we scale the time in hours. Here is h, hours, not hours, h. And it also can be in days. And on y, it is we scale the rainfall in millimeters. So, and again we scale discharge in cumex. Remember what cumex is? It is a unity that is representing cubic meters per second. So on a storm hydrograph, there are some key features like peak rainfall, which is the highest rainfall experienced, peak discharge, which is the maximum discharge that a river has experienced resulting from the precipitation that has happened, time lag, it is the time difference between the time of peak rainfall and the time of peak discharge. Remember, for the peak discharge to happen, there is need for rainwater to have flown into the river channel. So this happens after this. The difference between the times here is what you call time lag. Then the rising limb shows how quickly the discharge is rising, and the falling limb shows after precipitation how quickly the discharge is declining in a river channel. So as I said, on x-axis we put time in hours or in days. It's for a single precipitation event. Then on y we put both precipitation, it is shown by these bars, and the discharge, which is shown by this green curve. So this is precipitation or rainfall, and the highest experienced in this period, it has been this one. If you plot it here, you will see that it is almost 50 millimeters. So that is the peak rainfall or peak precipitation. Then as the curve goes high, from here before the precipitation started, you see the river has discharged. The discharge is scaled here is 10, 20, 30, 40. It was like, if this is 5, it was like 3 cumex, or 3 cubic meters per second. As the rainfall started to fall, discharge kept on increasing. increasing. So the whole of this part from here back to here, the whole of this is the rising limb, because it is showing how the discharge is rising and the precipitation was happening. And here is the maximum discharge experienced. If you can plot it here, we will see that it is almost 35 cubic meters per second. So this is our peak discharge. Another site here, from the peak discharge back to the normal flow of the river, is the falling limb. Maybe something else that I can talk about is the base flow, which is the normal flow of the river that is supplied by springs, excluding surface runoff. So this green is the discharge experienced by the river due to the surface runoff from the precipitation, but this red line shows the base flow, which is the normal flow of the river when the precipitation is not happening. And if you can see here, the discharge, the base flow keeps on rising gently, because as precipitation happens, more infiltration also happens, and more through flow and base flow can happen. So springs can supply more water in the river, then the base flow will be rising. But the green here is showing the result of surface runoff. So factors affecting the shape of storm hydrograph. The first one, there are very many, but here I have put some few. Precipitation intensity and type. So when the precipitation intensity is high, there is more surface runoff, because there can be quick saturation of soil moisture, or there can be infiltration excess overland flow. So that time there will be more water joining the river channel, leading to higher peak discharge, short time lag, and steep rising and falling limbs. And when it is the opposite, when the intensity is low, the shape of storm hydrograph becomes longer time lag, so if the intensity is high, the curve will be looking like this, and if the intensity is low, the curve will be looking like this. You remember, this is the peak precipitation, peak discharge 1, peak discharge 2. So if I plot here, you see the difference will be between this, and that will be time lag, so it will be short. If you compare with this peak, with this time lag here, where the intensity is low, the peak discharges here will be high and here will be low. So this is showing the river that has experienced higher intensity of precipitation, and here the river has experienced lower intensity of precipitation. Then if you observe again the limbs, the rising limbs here, this limb is steeper than this, and the falling limb here is steeper than this. For precipitation type, the precipitation can be liquid or solid, like rain and snow. Let's take the example of rain and snow. This will be showing the river that has experienced a liquid precipitation, which is rain, and this will show a river that has experienced solid precipitation, which is snow. Why? Liquid precipitation will quickly flow, while solid one will first melt before it flows, so it will take time, and that's why the time lag here will be shorter. You see, if we say that maybe if we assume that here is 3 and here maybe is 5, the time lag is 2. But if you keep on, this will be like 8. So 3, 8, the difference will be 5. You understand that the time lag here will be longer than the time lag here. And the rising limbs, this will be steeper than this one. And the falling limbs, this will be steeper than this one. And remember that this river is representing a river that has experienced a liquid precipitation, and this is representing a river that has experienced solid precipitation. Another factor is the temperature. So temperature influences evaporation. The higher is the evaporation, the lower will be the surface runoff. So it means that the river will receive less water. And if it receives less water, there will be a shorter peak discharge, longer time lag, and the gentle rising and falling limbs. While when the temperature is low, there will be less evaporation, more rainwater will flow to the river. That time there will be higher peak discharge, gentle steep rising and falling limbs, and steeper short time lag. This is a river that is surrounded by or is in a drainage basin with a lower temperature, and this is a river that is in a drainage basin with a higher temperature. Antecedent moisture. When there is higher antecedent moisture, there is a short time lag, there is a high peak discharge, and there is a steep rising limb, and vice versa. That's because with antecedent moisture, there is less infiltration and a high surface runoff. So this river will be showing that the drainage basin of this river has a higher antecedent moisture, and this has a lower antecedent moisture. Drainage basin size and shape. So normally when the drainage pattern is showing that the tributaries are close, that time the river receives the water very faster, and that time it rises its discharge very faster than when the river when the tributaries are spaced. So the shape goes with the dendritic or centripetal. Normally centripetal shapes result into higher peak discharges than parallel or dendritic or radial ones. So in that context, this river stands for a river that's in a drainage basin that is dendritic, that is centripetal, and this stands for linear drainage pattern or linear shapes. So the rivers here are spaced and here rivers are concentrated close to each other. Drainage density. Drainage density normally means the length of the rivers in a drainage basin. So length of rivers over area. So when the length of rivers and the tributaries is big, it means that an area is well drained. So water quickly joins the bigger river that is in that drainage basin, because there are more rivers draining away water from the entire land. So that time it means that the river will be receiving more water coming in, and as it receives more water as quick as possible, the peak discharge will rise faster, so time lag will be short, and there will be steep rising and falling limb, and vice versa. So this river stands for a river that is in a drainage basin with a higher drainage density. Many tributaries are bringing water in this river, and this graph is showing, is standing for a river that is responding to a drainage basin with a limited or low drainage density. In other words, there are very few tributaries draining the area. A high peak discharge here, steep rising limbs, and a shorter time lag, while here it has shorter peak discharge, gentle rising and falling limb, and a longer time lag. Porosity and permeability. These influence infiltration. So when they are high, there is more infiltration and more low surface runoff. So there is less. When these are high, there is less peak discharge, longer time lag, and gentle rising and falling limbs. But when they are low, less water infiltrates and more water runs over the surface, flows over the surface. So the river experiences a higher peak discharge, shorter time lag, and steep rising and falling limbs. So this has a lower permeability and porosity in the drainage basin, and this shows that the drainage basin has a higher permeability and porosity. Steepness of slopes. When the steeper slopes, the more the surface runoff. So there will be the shorter the time lag, and the steeper the rising and falling limbs, and the higher is the peak discharge. But the opposite, the gentler slopes, the slower is the surface runoff, and the longer is the time lag, and the gentler will be the rising and falling limbs, and the shorter will be the peak discharge. In this situation, this curve stands for a river that is in a drainage basin with the steep slopes, and this is standing for a river that is in a drainage basin with the gentle slopes. Vegetation. The thicker is the vegetation, the more is interception, and the more is infiltration. So this reduces surface runoff. If surface runoff is reduced, there will be longer time lag, gentle rising and falling limbs, and a shorter peak discharge. And while when the vegetation is limited, or it is a bare land, there will be more surface runoff, and there will be short time lag, steep rising and falling limbs, and a high peak discharge. So this curve shows, it stands for a river that is in a drainage basin with the limited vegetation, and this shows a river that is in a drainage basin with the thick or high vegetation cover. Land use. Here it goes with the urban land use and the rural land use. So built up areas which grow with the urbanization increase surface runoff, while farmlands or agricultural practices increase infiltration and reduce surface runoff. So urbanization leads to higher peak discharge, shorter time lag, and steeper rising and falling limbs, while rural areas with their agriculture, crop cultivation and animal grazing or or irrigation. They increase infiltration, but they reduce surface runoff. So there will be longer time lag. There will be gentle rising and falling limbs and short peak discharge. So here, this curve shows a river that is in urban area, and this is it is standing for a river in a rural area. So in our daily lives, what can we learn from this? There are some areas that are subject to flooding, especially those areas between steep slopes and in rivers close to in the floodplains of the rivers in urban areas. So at that time, people who are in those areas should avoid to settle in the floodplains, because as the discharge goes beyond the banks, there will be flood. So they need to settle on dry points. Again, there are some land uses that we should avoid in floodplains. Like, though agriculture is good in the floodplain, but not all crops can withstand floods. So we can encourage people to plant water-resistant plants like sugarcane. When it is flooded, it still can produce some produce that is needed by agriculturists or farmers.